talk is about incentivizing exploration by heterogeneous users by Chen, Frazier, and Kempe, and Bangrui will be the speaker. Thank you.
Hi, everyone. Today I'm going to present our paper, Incentivizing Exploration by Heterogeneous Users. This is joint work with my advisor, Peter Frazier, and David Kempe from USC. First, I want to talk about why we are interested in incentivizing exploration. So here is an example. Suppose there are 3 computers on Amazon's website. The first 2 computers all have a large amount of positive reviews, while the third one only has 1 2-star review. Then in that case, if all the other specifications about these 3 computers are close to each other, then a rational customer may not want to buy the third computer because it only has 1 2-star review. In general, Amazon and its customers have misaligned incentives. So customers are myopic and they just want to exploit, while Amazon wants its customers to explore. So without any incentivizing exploration, an alternative that seems worse initially may remain unexplored. So that's why we are interested in incentivizing exploration, and there has been a growing literature in this area. So broadly, this literature can be categorized into 2 categories. The first category involves no money transfer. They instead assume the principal has some information advantage over the agents. So as long as the agents cannot do a better job by themselves, they will just follow the principal's guidance. And the second line of literature assumes there is some money transfer, i.e. the principal will offer some money incentive to the agents so that the agents will do some incentivizing exploration. And our work follows the second line of research. So despite the fact that most agents have different preferences, all the existing literature assume users have homogeneous preferences. And as far as we are aware of, our paper was the first paper to study incentivizing exploration with heterogeneous preferences. So this heterogeneity presents a new challenge. If we go back to the previously mentioned Amazon's example, each customer may prefer different computers to fulfill their specific needs. On the other hand, Amazon doesn't know which customer prefers what computer. So neither the customers nor Amazon itself can do a good job. They need to somehow coordinate with each other in order to maximize the cumulative social welfare. And that is exactly the problem we are trying to address in our paper. Based on our analysis, we show that this heterogeneity not only presents a new challenge, but also provides free exploration. I will explain more about what I mean by this. So here is our problem setting. We assume that the agents are arrived to the system one by one, and agent T has a linear utility function with a preference vector theta, which is the d-dimensional vector drawn from a known distribution F. There are n arms in the system. Each arm has an unknown d-dimensional feature vector, denoted as ui. Every time you pull the arm I, it will return you a vector-valued outcome which equals to ui perturbed by an independent sub-Gaussian noise. Everyone has the same amount of information. Both the agents and the principal can observe this UIT hat, which equals to the average of the arms pass pulls. As I said before, in our work, we assume that the principal will offer some money payment to the agents, and we use this CTI to denote the payment for arm I at time t. And with this incentive, the agent will just pull the arm that's maximizing its myopic linear utility function plus the incentive. And as a principle, our goal is trying to come up with an algorithm that can minimizing the cumulative expected regret while making a small cumulative expected payment. So that is our goal. So now let me introduce our algorithm. Our algorithm is very simple, but we need a definition called payment eligible. So informally, our arm is called payment eligible if without any incentives, the myopic pulling probability for that charm is below some threshold, and we haven't pulled that charm for a long time. So this is a very informal definition. And with this definition, we can introduce our algorithm. Our algorithm is as follows. So for every time t, we check whether there are any arms that are payment eligible. If there is, we just pick one arbitrary payment eligible arm and offer that arm a large enough payment to raise its probability of being pulled to above some threshold. And if there are no arms that are payment eligible, we just let the agents play myopically without offering any payment. So this is our algorithm. To analyze our algorithm, we need 3 key assumptions. The first assumption states that every arm is somebody's best arm, like each arm is preferred by at least p fraction of users. So this is the assumption that guarantees that there is enough heterogeneity among different users. The second assumption states that theta has a compact support. So theta here is the agent's preference vector. And the third assumption states that there are not so many users who have near-type preferences. More specifically, if we let this QZ to be the cumulative distribution function of those users who have whose utility difference between their best arm and the second best arm is less or equal to Z, then there exists a constant L such that QZ is bounded about by L times Z for some small enough Z. So based on the assumption in our paper, as long as the density function of the user's preference distribution is bounded about by a constant like this, then this L is finite. In particular, if the user's preference distribution is discrete, look like this picture, then L equals to 0. So now we can, I can state our main result. So with the previously stated assumptions, our algorithm or policy can actually achieve a constant cumulative can achieve an expected cumulative regret of a constant plus n log t to the third with expected cumulative regret with the expected cumulative payment bounded by a constant. So one thing to point out is that this constant is actually very large. It is exponentially dependent on 1 over p. We can actually improve this constant to polynomial dependent on 1 over p if either the agent's preferences are discrete or we have a lower bound about p. There's one special case that I think worth mentioning is that when the user's preferences are discrete, i.e. L equals to 0 in this case, the expected cumulative regret is actually bounded by a constant. It's n squared divided by p, using an expected cumulative payment of n divided by p. So this is very different from the traditional multi-arm bandits problem, which says that the regret is at least log t. So here is the intuition behind our result. So when the user's preferences are discrete and there are no users who have near-type preferences among arms, then after each of the arms has been pulled a sufficiently large amount of time, you are basically already know what are each arm's attribute vector. Then for any particular arm I, every once in a while there will be an agent come to the system who can correctly identify arm I is his or her best arm, and he or she will just pull that arm myopically without any incentive. And that pool will provide free exploration for all the future agents. So that's what I mean by heterogeneity provides free exploration. And because of this free exploration, we can actually achieve constant cumulative regret with constant cumulative expected payment. And when there are some agents who have near-type preferences, the analysis becomes more complex because any small misestimate of the arm's attribute vector may lead to a mistake or regret for those agents. So that's why in our general result, we have this extra log t term. In fact, in our paper, we provide the example to show that regardless of your incentivizing strategy, the best regret you can achieve is log t. So our regret bound is log t to the third. In a sense, our regret bound is kind of tight. And these are the general results for our paper, and I'm happy to take any questions if you have.
So questions, common?
So when you say regret, are you meant is the payout of Amazon the same as the payout of the user for each of the users, or is there some different payout between the principal and all the agents?
You mean the regret is defined as the if the user can correctly identify his best arm, then that is the maximum utility he can achieve, right? Minus the utility he actually achieves. So that is the regret. And
The user and the company is aligned.
yes, it's aligned. Yeah.
Other questions, comments? Okay, if not, let's send the speaker again.
Thank you.